Okay, we're going to have a look at the work of two men. I can't quite remember the spelling. Called Meselson and Stahl. If I've spelled that wrong, it means the same thing. So Meselson and Stahl came up with a hypothesis for how DNA might replicate itself. They said it could be conservative. It could be semi-conservative, or it might be something that they called dispersive. Now, in conservative, what they said was that your DNA would stay the same, but then you would make one whole new strand of DNA. So you keep the original one, you make a whole new one, hence the name conservative. Semi-conservative, we've already discussed, we know this one to be true, but this is the evidence for it. So how do we know that it's true? And that's down to these guys. So what they said was that your DNA would split each old strand, each original strand would act as a template for a new strand of DNA to be made against. And so the new DNA will be half original and half new. Here you get a whole original and a whole new. This one is half original, half new, half original, half new. Dispersive, what that says is that your original DNA gets mixed up with the new. So what you end up with is two strands, but they're very mixed. And so you would end up with, you get the idea. Half and half. Okay, so you chop up this and you mix it and distribute it in with new. So they wanted to know which ones of these hypotheses was true. So they came up with a really, really good experiment, a really very lovely experiment. It works very, very well. They put some bacteria into medium, so just like a broth, like a liquid, containing nucleotides. So the nucleotides, remember, you've got your sugar with your phosphate and you've got your nucleotide base. Now, they gave them nucleotides containing nitrogen of a particular isotope. Nitrogen exists in two isotopes, N15 and then a lighter version, the version that's predominantly in the atmosphere, which is N14. So they grow these bacteria so that all of their DNA contains this heavier N15. So that's what all of this original DNA is. Now you can do something called, or spin DNA on something called a cesium chloride gradient. And so when you do that, when you spin cesium chloride, it forms a density gradient. So it's really dense at the bottom, and then it gets less dense. If you extract DNA from cells and spin it, so put it in a centrifuge and spin it around very, very fast, the DNA will find its density and will form a band. So this N15 will form a band down there somewhere. If you spin the N14, it'll form a much lighter band. It is actually lighter. So it'll form a band much further up. So let's just colour that in a little bit more. Okay, so what they did is they took the bacteria, let them make some DNA containing this heavy DNA. And then they took those bacteria out of that medium and put them into medium where any new DNA they made would have to be made with N14 nucleotides. So instead of these ones, you'd have the lighter ones. So all new DNA would be light. So if it was conservative, what you'd get here would be a band for N15. Same with this one. You get a band down there for N15, and with this one, you get a band down there for N15. If it was conservative, what you would get is a band down here for N15, and this one would form a band up here for N14. Now, when they did this experiment, they didn't see that. They did not get that. So we know it cannot be conservative replication. If you look at this one, these are bonded together. So these two strands will move in the cesium chloride together. So if that strand is 15 and that strand is 14, we're going to technically call this 14 and a half. And same with this one. So if you spin this one in cesium chloride, you'll get one band. They'll both move to somewhere between, halfway between 15 and 14. And that's exactly what they did see. But if you spin this one, remember this one is an equal mix of 15 and 14, you'd get the same thing. You'd get a band halfway between 15 and 14. And again, that is what they saw. So they couldn't quite work out from one experiment, one lot of DNA, if it was semi-conservative or dispersive. So what they did is they let these grow again. Now, let's have a look. Just rub these out for a minute. So at this point, it could be either one. So they grew these again. So again, any new DNA would have the N14. So if we just have a look at this strand, you separate your two strands. I've got red pen on my floor. And then you separate these strands. This one to there, that one to there. Now remember, they are in a medium that only contains N14. So all new strands made against these original templates will have 14. 14 DNA. The lighter DNA. Now if you do the cesium chloride gradient for this one, what you find is that these two are still 14 and a half. These two are now completely N14. If we do the same with this one, so again, you're going to take these original strands, break them up, and mix in some new DNA, but the new DNA will be N14. However, this 15 gets equally distributed. So that's one strand, that's two strands, that's three strands, four strands. But all the new DNA gets mixed in with that. Somehow. So you can see every one of these strands has some N15 in it. So if we spin this one, it's not going to be N15 because it's not all N15. It's not going to be any bands for N14 either because none of these are completely N14. So what happens is that where it would have been N14 and a half, it moves up slightly from it because it has more N14 in it than N15, but it's never completely N15 or N14. Now when they did that experiment, that's not what they saw. They did see that. So they had proven that it was semi-conservative replication.